Sir, we'll go live in 1 minute.
Yes, sir.
Pankaj Bhande, sir, are you there online?
Hello.
Pankaj Bhande, sir.
Yeah, he's there. He's there.
Yeah. Yes, I'm here.
Yes.
It's already late. Where's Arjun?
He's looking for universities, right? Maybe he's held up there.
You look so tense. By the way, did you get to choose the university?
No, I'm unable to find a university that meets my requirements.
Whoa. Meet your requirements? What exactly are you looking for?
I'm looking for a place that gives me an opportunity to grow, to excel, to invent, and to innovate. I want to be a part of an institution that paves my way to discover myself and to witness the world moving forward in technology. I want to go to a place that sets a futuristic pattern of education filled with ideas and radical performances. Basically, I want to live my dream.
Dayanand Sagar University. Live the dream.
So we are good to go live.
Yes, sir.
Good afternoon to all of you. A warm welcome to all the students who have registered via Uni-Gauge for the examination with Comet K, or for the entrance examination with Comet K. We are associates with Uni-Gauge, and we have taken the opportunity of inviting all of the students for this exclusive webinar on the topic, the changing era. Emerging technology bringing trending job opportunities in mechanical engineering, electronics and communication engineering, as well as aerospace engineering. While we see that more than 15,000 students have registered with Uni-Gauge, we have been getting a lot of requests from various students to help them to choose the stream of engineering that would be preferably good for them. They want us to make a choice. And we felt that instead of talking to one student, why don't we educate students on what's happening today? On one side, you have students who are rushing towards computer science engineering. And on the other side, you have the industry where the demands are slightly moving. It's becoming like a multidisciplinary approach where even the companies today are looking out for varied students with a kind of multidisciplinary approach, where we are seeing the jobs are coming back in demand in mechanical engineering, with some new age specializations. There's great amount of demand coming in our placement department requirements on electronics and communication engineering. People are talking about robotics, people are requiring about automation, people are talking about VLSI, people are talking about communication technologies, people are talking about AI and ML integrated either with electronics or with aerospace or with mechanical. And it's been a beautiful amalgamation of technologies from these core areas of engineering, where we are seeing the demand is again coming back. The demand which was there 15 years back is slowly arising, and the number of job opportunities in the given areas in this webinar is increasing. And this is the reason we thought of getting in some of our expert panels from the industry so that we could have this particular webinar for all of you. So here we are today on behalf of Dayanand Sagar University, bringing out this exclusive webinar on the changing era with the amount of jobs and technologies via mechanical engineering or electronics and communication engineering and aerospace engineering. Through this webinar, for the students from Uni-Gauge can take the advantage of this, and post this, it could give them a good background for them to, as a food for thought to think upon, and then come and select the kind of program that they would want to do. This webinar will also tell you about how to choose a program, how to look at the technology part of it, and how should you look at selecting a good university which can offer these kind of programs to. So with this, I would like to take the opportunity of inviting our speaker number one. I'd like to introduce our Honorable Vice Chancellor, Dr. K. N. Murthy. Sir is the Professor for Computer Science Engineering and the Vice Chancellor at Dayanand Sagar University, Bangalore. Sir has been the former Vice Chancellor at PES University. Sir holds a bachelor's degree in electrical power engineering and a master's degree in electrical engineering from Indian Institute of Science, Bangalore. Sir also holds a PhD in computer science and engineering from Indian Institute of Technology, Madras. Sir has worked as a research specialist in parallel computing at New Mexico State University, US. Sir is currently the member of Karnataka State Higher Education Council and also the academic senate member for IIIT Dharwad. I would like to invite Sir to set the context and to share his views on this particular webinar. Over to you, sir.
Thank you, Mr. Shinde. Good afternoon to all the participants in this webinar. Also, respected co-panelists, Mr. Shinde and his team. I'm extremely happy to be a part of this event, sharing some of my thoughts and also making few opening remarks to set the context for this webinar. As you're aware, this webinar is an exclusive one for core engineering. These webinars have been organized by Dayanand Sagar University to provide awareness to all the aspirants so that they can make an informed choice of pursuing their engineering career. First and the foremost thing all of us need to understand is about engineering itself. Engineering is ruling the world today because it provides real-time solutions to various problems. Engineering has positive effects on the lives of the people. Engineering utilizes the knowledge of science, maths, logic, and experience to introduce innovations. The progressions in these innovations are normally referred to as recent trends in engineering. If you look at the recent trends in engineering, there's a tremendous changes that are happening in the recent past. In the last 3 to 5 years and the next 5 to 10 years, there will be tremendous changes that you can expect. Every field of engineering will have lots of opportunities. One prediction has been made is that the total number of jobs that are available in the future, in the next 5 years, is going to grow from 41 million to 191 million in all the branches of engineering and other sectors. Before you make an informed decision to pursue a program study in engineering, you need to know about them very, very clearly. We have requested few experts to talk about their experience and their knowledge in terms of mechanical engineering, electronics and communication, and aerospace. Possibly at the end of this webinar, you get a fair idea about the kind of opportunity that exists in core engineering. All of us need to understand that core engineering is going to use the recent technologies to solve their real-time problems. Some of the changes that have happened in the recent past are that the paradigm shifts are happening in terms of the graduating students. If a student is going to graduate from the portals of a university or an institute, earlier, the student needs to have knowledge and skills. Possibly in the future, the student going out of the portals of the university or the institute needs to go with an enterprise idea, an idea to start an enterprise. That is the kind of requirement that may come up in the future. That's what I'm predicting. What I would do in the next 3 to 5 minutes is to tell you briefly about the 3 things that you need to keep in mind before selecting a program study. First one, you need to know about future work requirements. Second, you need to know about which program study to be pursued for making a career. The third one, which university to study that program study to get that opportunity that exists in the future. Let me start with the first one. The future work environment will be far different from what we see today. One, the existing jobs and job roles will go through a metamorphosis, would go through tremendous change in the future. Therefore, the existing jobs, many of them get automated. The new jobs get created. That's one prediction that we made. Second, technology is going to play a major role. What technologies? Technologies like AI, artificial intelligence, robotics, the 3D printing, blockchain, machine learning, several others. They are not the technologies in computer science alone. They are going to be technologies used in every other branch of engineering. In every core engineering, these components are being used. These are technologies. One thing is very clear in the future is that computer science or computer technologies are being used everywhere across the domains in any walk of life. That's one prediction that's there. Second, in the future, reskilling, upskilling, and transformation learning becomes very, very important. The third thing that you need to remember, the knowledge of technology is inevitable, is very, very important. Therefore, while graduating from the school, you need to know some technology and reasonably good amount of expertise in that. Now, coming to program study, which one to study? Is it mechanical engineering? Is it electronics? Is it computer science? Or is it aerospace? Or any other thing that you're going to talk about? Is it civil engineering? All that you need to do is you need to make an audit of your talent. What is the talent that you have? Are you good in mathematics? Are you good in physics? Are you good in chemistry? Are you good in biology? Decide about that. First one, what you're good at. Second, what's your passion? What exactly you want to be? Then these two things will decide the program of study that you would like to pursue or you need to pursue. This other thing that you also need to look at is not only the branch that you're going to choose. You can also do the study in other domains of your interest. That's the flexibility that you have today. For example, you are going to do a mechanical engineering degree and you can also do a minor in computer science. You can do a mechanical engineering and do a minor in electronics. Therefore, parallelly, you can do two degrees. That's dual degree, double degree options are possible. Therefore, the options are not limited to the branch that you're going to select, the branch you're going to study. That's one thing which you need to remember. Program study, you decide based on your passion, based on your thing, and you don't have to worry about the opportunities. Opportunities are going to be plenty in every field of engineering, in every field of study, be it management, be it finance, be it commerce, you have plenty of opportunities. Therefore, opportunity-wise, we don't have to worry about. The other thing that you also need to look at the university. Which university is the right university to study? A university which is ready to experiment. A university which can offer you multiple options. A university which provides you that flexibility. University that gives the kind of environment for experiential learning. Therefore, most importantly, you need to select a university or a institute which has understood the national educational policy reforms quite well. National education policy reforms purely the flexibility. Means doing a mechanical engineering and doing computer science together is what is going to be the thing. The second, the education that remains with you for a longer duration, that university must be selected. Means you need to learn things in a much better way than the normal. It's not from the concept of getting a degree. It's from the concept of, from the point of learning the concepts quite well. That's what is exactly required for the future. And you also need to join a university which will offer an opportunity for multidisciplinary learning. I'm sure the experts would give you a lot more information. I think the experienced experts with a lot of background, lot of knowledge, they share their experience working with the technology. By the end of this particular webinar, you will be fully convinced core engineering is no way inferior to computer science. Core engineering is the one which is going to dominate. It's also been predicted that the core engineering will get its opportunities, will come back with a lot more job opportunities than before. Possibly the salaries of the people of the core engineering are comparable to any other graduates in the future. I thank the organizers for inviting me to make few opening remarks, and I request the experts to take over and tell you very clearly what exactly is there in mechanical engineering, electronics, and aerospace. And Dynam Sagar University is going to be the university which is going to try out all the things I mentioned. Multidisciplinary learning, trying to experiment, trying to provide the flexibility. All these things are going to be done by Dynam Sagar University. I'll stop here. Over to Ms. Shinde for further proceedings.
Yeah, thank you so much, sir. It's always a pleasure to listen to you and the wonderful guidance given to students in terms of a different approach towards engineering and towards planning this, the kind of stream that they need to take. Thank you so much. So students, today we have brought in a series of experts from the industry. It really takes a time, and it's a fortunate activity for all of the students to listen to these kind of experts from the industry who on a Saturday have devoted their time to the Anand Sagar University to share their thoughts, their success stories to the students. So here we are. We start with the mechanical engineering. Though I use the word mechanical engineering, but mechanical engineering has far advanced. And today at DSU, when we talk of mechanical engineering, we talk of 3D printing, the hybrid and electric vehicles, we talk of robotics, all of these coming in as new age specializations into the program. So here I take the opportunity of introducing our distinguished speaker for the day, Professor Dr. Suresh Nagesh. He is a PhD from Drexel in 1992 in mechanical engineering in computational mechanics, and IIT Kanpur alumni who has passed out with a master's in solid mechanics in 1987. After his master's, he worked for a year and a half at Indian Space Research Organization. For PhD, he worked on a Boeing-sponsored NASA ATCAS, Advanced Technology Composite Aircraft Structures project. Most recently, he was the managing director for VOITH, and set up a technical center to support Airbus activities in stress and flight physics across the globe. He also supports Quantum Point Private Limited, based out of Washington, D.C., and helping Quantum set up their design and tech center based out of Bangalore. A warm welcome to you, sir, and over to you to give the students an insights on what is it that they have today in tech plus mech and the way forward. Over to you, sir.
Thank you so much, Srinivas. I'll start sharing the screen.
Yes, sir.
And kindly let me know if you can see it. Okay.
Yes, sir.
So
Screen is visible. You can go to the presentation mode.
Yeah. So first of all, I thank my very close friend, Dr. K.N.B. Murthy and Dayanand Sagar for providing me this opportunity. And I have been counseling students for a very long time. And everybody has the same question. Why not IT? No, because the students are wired from their high school days that IT is the only way out. A lot of job opportunities, of course, and a lot of money. Maybe when I was getting as an undergrad from IIT Kanpur way back in '85, if this sort of opportunity was there, I don't know, maybe we also would have ended up with IT. But our professors took us through a different route, and they said that, guys, listen, you guys code and code and code. Yes, we have coded hundreds of thousands of lines, some of us, our era people. And even today, we use the HPCs, we call as the high-end performance computers, much more than what a computer science person would do. And in today's world, as Dr. Murthy said, the possibilities are infinite, opportunities are infinite. You need to have a passion about what you want to do. And I cannot go, more than 10 feet from my side, because I have my own son whose IIT JEE percentile was 99.973. And he could have got anything he wanted to, but he said, Dad, I want to do computational fluid dynamics. That's my passion. And my wife, who is also a physics major, we both said, it's up to you. You decide. Today, last September, he finished his PhD from Duke University, currently working with Pratt & Whitney on CFD. Okay, that is the passion. Okay, you don't have to think or worry about what others do. Think about what is that you want to do. That's very, very important. All of us, especially, we were a little bit fortunate that we came from at that time, IIT Kanpur was number one in this country, and our professors were too good in terms of trying to tell us what is that we want to do. In fact, they sent us to the professor whom they thought was good based on our background. That used to be our era of things. And this is what we want to bring back and say, guys, listen, I mean, anytime you want or you have a question, all of us are available. Everybody in this panel are available, to give you advice. At the end of the day, you have to decide what you want to. And I think Murthy brought out a very good point that whatever you study today should carry you forward for another 30, 40, 50 years. Okay. And that's the foundation that we are trying to lay now. And this is something which is very, very important to understand, that what I do today should take me for a very long distance. So let me say this to start with, that today everything is multidisciplinary. You can no longer call yourself, a mechanical engineer or a computer scientist or an electrical electronics person. All of us have migrated. Today, I had the opportunity given to me, and I have led institutions and still trying to support institutions where multidisciplinary is the theme. So that's the reason why we talk of dual degree programs these days, a combo of things. But let me make it very clear. At the end, I will try to define to you what engineering is. Okay. But at the beginning, let me tell you, every pen, pencil, paper, the automobile that you drive or the aircraft that you fly, everything has an aspect of every engineering in it, and everything starts with materials. So a good engineer to me is also a good material scientist, because unless I know what to build, how to build, why to build, and with what I should build, then I cannot build something. It's like picking up a shirt. The starting raw material is basically a fabric, and which is designed, engineered, and stitched into whatever shape and form that you want to wear. As simple as that. And then there are two important parameters that define any system. Okay, for example, you are using a pencil. So I ask all my students and whomever I interview, saying what are the only two requirements that anything that is designed and used and built in this world have to satisfy. And unfortunately, in the engineering curriculum, this is not taught. So in the very first class, I asked this question. Then a lot of students give me a lot of answers. But some of the answers that were given to me by my teachers. So there are only two requirements, something called a functional requirement and something called as a performance requirement. Anything has, so for example, you take a pencil. The functional requirement is for it to write. Performance requirement is the lead should not break. Now ask the question, how did I make sure that the lead did not break? That is core engineering. I need to choose the right material. I need to choose the right process. I should use the right design. And then I have to integrate all that into this thing called a pencil, and I have to make it right. You take any product in this world, whether it's an automobile, whether it's an aircraft, whether it's your smartphone or the laptop that you're saying, everything is actually engineered. Means that engineer is a product creator. You are creating a product, and the product has many entities, inside it. A lot of mechanical engineering. To open your laptop, you need a hinge, and then what is this? This is mechanical engineering. Your whole body is a combination of mechanical, electronic, chemical, you name it. God has devised this in a way that it is a combo of everything. I move my hand, it's mechanical engineering, right? Today, we move the hand using sensors. That is where all robotics, etc., come into picture. And we are going even beyond that today to the concept called digital twins, wherein I try to create, a virtual representation of the real system. That is where AI, ML, etc. that we talked about, comes into picture. But then I cannot use the same AI and ML knowledge from the IT industry in engineering, because first of all, I need to know, the product. What is it? What can it do? I'll give you some examples. For example, if you buy a car, what is that you're looking for? You are not paying money for something. Of course, it has to take you from point A to point B, which is its functional requirement, but its performance requirements are many, for which all of us pay for. It has to be safe, it has to be durable, it has to be quiet, it has to give you fuel efficiency, so on. And now when you think of each one of these, to start with, everything is mechanical, driven by sensors and microcomputers, okay, to perform the way it should perform. And then at the end of it today, some of us are working with guys like Mercedes in developing digital twins for the transmission, digital twins for the fuel systems, digital twin for the lighting system, which ensures that at any point in time, enough data from the system is being collected, analyzed, and you're taking some corrective action and make sure that it performs the way it performs. So to me, today, it is a culmination of all, branches of engineering. And that's what I wanted to talk about. And I put the digital twin as an integrator of all core engineering branches, along with computer science and engineering. And as Murthy clearly said, you definitely need to have a good knowledge of physics. Math is the knowledge of physics, so I need to have a lot of mathematical knowledge. I need to know about materials, and of course, I need to know about the product itself. And then this is a challenge and the opportunity, that core engineering brings into. It's a passion. I want to create something. As human beings, we want to create something. We want to create something better. And that's how all the technologies have developed over last 100 years. And today, of course, we talk of electric vehicles. And if you see the complications, battery management systems, battery itself is a huge technology, and that is pure materials and chemical or chemistry. And then motors, controllers, and of course the design and lightweight materials to make it as light as possible. I mean, it's just an amazing combo of. So let me just give you a little bit. I have chosen automotive because I started with Ford Research in US a long time back in '92, and then things don't change much. But as Murthy said, technology is making things better, and so you can work from material to the product and the engineering process in between, which is one of design, build, test, validate. There's so much to this. One generation of life is not sufficient to even actually work on one aspect of these lines that I have put here. So for example, if you are an automotive engineer, you can work on just the design of automobiles, which are fairly complex by nature. And then if you want to do some virtual simulation, you can work on, we call it CAE, computer aided engineering, or you can work in manufacturing, or if you're an electronics guy coupled with mechanical, we call it mechatronics these days. And then so you can work on the embedded systems, etc. Electrical people also have a lot to do, especially in automotive and aerospace. And I know my close friend, Dr. Sharath, will tell you, in the aerospace industry, even saving 1 gram of copper means a lot. And how much of work is being done on the electrical side of the system, because a typical aircraft has miles and miles and miles of wires inside. And then it is even crazy to imagine how much of wire that is there and how we manage that. Okay. And then, of course, if you want to bring in the concept of IT into engineering, you can do a lot on PLM, project lifecycle management, and which is integrating of data, engineering data across globe, because today manufacturing happens all across the globe, design happens across the globe, simulation happens across the globe, and we need an integrated single window system to integrate all the people who are working together and create one single product. And then it's a huge opportunity. Okay. And some of us have migrated now last few years into digital twin technologies, which is what the whole world is looking at. And then and some of us have actually created physical digital twins, which have gone into some of the best German machines. Okay, so we can talk a lot of this. If you wish to, we can have a separate discussion on digital twin technology, a conglomerate of all engineering. Okay, and my team on digital twin includes everybody from mechanical to electronics to embedded systems to computer science guys, some real top ones. Okay, so in nutshell, you can work on concept design, detailed design, or design if you are getting into the design mode, or if you get into simulation mode. One life, as I said, is not sufficient. You can be an expert in durability, you can expert in NVH, expert in CFD, or expert in crash. I mean, this is just unbelievable. And every single company in the world who are involved in automotive or aerospace or even any other engineering development will have to do all this. I have not included here electromagnetics on purpose, but today electromagnetics, EMI, EMC requirements, so much is required on each because every single system has a lot of electronics that goes into it. Okay, although ultimate thing is it has to drive something mechanical. Okay, I can update this slide and share that with you, but the opportunity is just endless. Okay, so at the university we have groups who are being trained. The students trained from third semester onwards on every of these technology depending upon their passion. You can tell us that I want to be in automotive design. We will train you in automotive design. You want say I want to do some simulation, fine. Somebody says I want to build this, perfectly fine. It is even better because you learn a lot when you build, and it's today everything is a teamwork. You cannot say all alone I will do everything. It's not possible. Okay. So this is a vehicle that we are building right now for quantum, and this is completely driven by a smartphone technology. Somebody wants to come and have a look at what this technology is, please come down and you will see some amazing things that are being done on this one. Okay. Or if you want to work on the ride and handling of these systems, whether it's suspension, steering, braking, automotive is the best, one of the best, engineering domains to be because it incorporates in it everything. A lot of technology is developed in the automotive, which then gets into aerospace and other technologies. So electric and wave, this is one of not only a passion for me and Dr. Murthy, but it's what the world needs right now. For example, functional safety of vehicles. I can tell you right now, I can vouch that there are only 6, maximum 7 people whom I know on the globe, okay, who are good at functional safety. And today in Bangalore, Intel itself wants close to about 1,000 people. Microchip wants about few hundred people on functional safety only. And then they keep on asking me, but I tell them I don't have anybody. Okay, huge requirement, huge opportunity. They pay you really well, but unfortunately, across the globe, we don't have these people. So there are a lot of opportunities where you can actually work in core engineering and be very, very successful. And if you want much more information on all these technologies, you can talk to us. Digital twin, of course, is my passion right now. Integrating physics into analytics. We call it as physics-based analytics. This is the future. Every OEM in the world by 2025 are required to provide digital twin of their major subsystems and systems. So this is where really the AI and ML are being applied left, right, and center, but there are huge challenges in engineering. You talk to any of my computer science friend, he will say, I need millions of sets of data points. And I'll tell him, hey, just stop. I don't have millions of sets of data points. I only have a few dozen sets of data points. That's where computer science stops. And we need something called as sparse data analytics. How do I take minimum set of data, but still be able to predict what is happening with the system with a high level of probability? And this is where the challenge is. Very few people understand what this challenge is unless and until they understand core engineering. I need to know my performance requirement of my product and how is it going to perform over years of time. Not just, today it may perform well, but tomorrow it may not be performing well. I need to know if something is going to go wrong ahead of time. It's called as the predictive maintenance. And then if something goes wrong, am I able to predict how long can this run? That's called as the remaining useful life of the system. Huge applications, not only in engineering, but also in medical domain. In fact, I'm not even covering computational biomechanics, which is a very, very large domain of activity. And then we would strongly think about, offering a minor on computational biomechanics. Huge opportunity. Lot of medical systems people are asking me on that one, and the same medical people have a lot of thing on the electronic side. It's called the medical electronics, and then you can create products, which save lives. And then it's a fascinating. Again, everything has to do with core engineering. I will not read through this, and some of this we are going to share with you, so you can come back with questions. And this is an actual digital twin we have developed for a rotordynamics application for Siemens. One and only digital twin on the globe. So 5 years back, if you had asked me, do you have any idea of digital twin? My answer would be no. And then it took about 5.5 years. Dr. Murthy knows it very, very well. And there's one amazing research activity that we have done together. And then we actually created world's one and only digital twin, which this year is going on Siemens missions. We made it completely wireless as well. So, and this is a technology of the future, combination of mechanical, electrical, electronics, and computer science in one. And then my dear friends, core engineering has a lot of value. It will take you for the long run. IT takes you for the short run. This is the basic difference. Okay, and we are living examples of people who have been working for the last 35 years, and will continue to work till we live. And that is the opportunity that core engineering has provided us. Only thing is that you have to march with time. You have to learn. Learning is a daily activity, and we have to learn to change and try to bring in technologies that are there in the other sphere into your passion. And that is precisely what we want to offer. Okay, and this is where we want to differ from the rest of the crowd. They can talk, but we will do. Okay. Like that, we are today working on digital twin for manufacturing, etc. And there's a huge opportunity in automotive electronics. I will leave it to our ECE people to talk about it, but I mean, this is another amazing thing. It's pure out of passion that I do some of these things, but here the opportunity is just endless, because every day the electronics is changing. With the change in electronics, the hardware changes, the software changes. Then, of course, as I said, the functional safety of all these things, it is just one heck of a job. And then this is absolute core, and core engineering has nothing to do with IT. Of course, we use IT to complement and supplement a lot of technologies, but imagine designing a VLSI chip for an automated car. Just think about it. Nobody has done it so far. And I have 9 years patents myself, and I'm a strong believer in invention and innovation. So core engineering provides you with that opportunity to invent, have something against your name, and then I'm also some sort of an entrepreneur. So I love to start up things. In fact, I have started 5 centers in this city called Bangalore, and I'm trying to develop one more research organization again from scratch. Let's see, that will be probably my last exercise, but yeah. So there's a huge opportunity. Okay, and then there are many companies. All of them are sitting here. Just one touch on the aerospace. These are the 6 main domains in aerospace. Sharath is going to take care of it. But let me tell you, each one of these domains is probably 10 lifetimes. Let me put it that way. Sharath can watch for me how many aerodynamics experts we have in this country. The few whom we know are already perishing. But the next generation, we ourselves are struggling to find the good ones. And we really have to develop this because India needs it. I was at DRDO yesterday, and I was supposed to be there yesterday, but I could not go. But I will tell you, because of indigenization in this country, amount of projects that are going to come in aerospace and defense is mind-boggling. I'm telling you, is mind-boggling. And then we don't have the set of intellectual infrastructure to handle this. Huge opportunity in all these 6 domains. And I can vouch on this one because I'm a part of some of those committees, and I see it on a daily basis, a huge amount of opportunity for everybody. So please think about it. And I want to just take you to the last two slides. This I have created just to tell you that every single box here is somebody's lifetime thing. You can work for 30, 40, 50 years, still you live on each one of those boxes. Highest level of integration of IT into engineering is what I have tried to put in here and what the future is looking at. Within 20 minutes, I'll not be able to cover this, but if somebody is really interested, we can organize a separate talk and I can take you through each of these blocks. It has taken me at least about 20-25 hours to create this one single slide, but this single slide captures everything that is happening in the industry right now, integrating core engineering with IT. Lot of people, I just picked a few of them here, mainly from the automotive domain, but you name it, apart from this Boeing's, Airbuses, Pratt & Whitney's, everybody are here right now in Bangalore, in our country. And then you can be a part of any one of them and you can be there for life. Your kids can be there. You know, that's the opportunity that this happens. As a last slide, I thought I will leave you with some thought process. In fact, when we were of your age and when we actually joined, when we were in the first day at IIT, so they keep on asking the same question, what is engineering? Please define. So in fact, I didn't get any answer till I went to U of Penn, and in fact, I started my PhD at University of Pennsylvania, then moved to Drexel because my boss moved there. And I was taking a fatigue course way back in 1989. And again, the professor, those days, it was all we call as slides, slide projectors. So you write everything in hand, project it on the slide projector. So he asked the same question, define engineering. And all of us, a few PhD students and a lot of master students, everybody, we gave our answers. The one that impressed me most was the answer given by this professor. I still cannot forget this. And if somebody asks me what is that you're trying to do and what is your CV or resume, this is actually my CV or resume. So engineering is the art of doing things approximately right and being exactly wrong. Give it a thought, and that's exactly what this is all about. And I will stop here. I'm open for questions. And the first talk is always a tough talk. So I hope I energized you guys a little bit. I know the other ones are too good and they will give their perspective. So,
Sure, sir.
Any questions?
Thank you so much, sir. Thank you so much for this lovely insights on how the new age mechanical and technology together, MEC plus tech, is going to give a new dimension to the aspiring students. Thank you so much for the deeper coverage and the insights.
I'm sorry it took a little bit more time, but
no, sir, no issues, absolutely. Thank you so much.
Thank you for the opportunity. Thanks everybody.
Thank you, sir. Yeah. In fact, now we move to the next and something very interesting for students. Electronics and communication engineering has been here from years and years, but there's been a lot of development happening in these areas. Even if you look at our own curriculum that we are offering at Dayanand Sagar University, we talk of electronics and communication engineering with new age specializations. And specializations ranging to automotive electronics, electronics in agriculture, evolution of telecommunications, IoT and wireless sensors, and wireless sensor and network. We talk of microcontrollers and microprocessors based design. It's more and more specialization is coming, more and more demand is growing, more and more applications are coming in, and hence, on this particular emerging technologies with electronics and communication, we have three of the experts from the industry who have joined us today, and we have something wonderful that will be presented to you. I take the opportunity of inviting our first speaker for showing us the ways and the opportunities with the electronics and communication engineering. I'd like to introduce Professor Joy Prabhakaran. He is a consultant to Tata Elxsi and an advisor to Atlas Silicon. He is a professor at KSIT and an adjunct professor at IIIT Bangalore. Professor Joy did his BTech from IIT Kharagpur and his MS from Michigan Technology. He started his professional career in 1989. He has worked for various organizations, including CDAC, Honeywell, Technicolor, and Yahoo. He ran his own company, Techline, for about 10 years. He has 2 patents for his work at Honeywell, 1 patent filing for his work as a consultant at TCS, and 2 that he filed as an individual inventor. He was also part of the patent review board at Honeywell. In 2011, he moved out of a full-time career and started working towards his PhD at IIIT Bangalore. He completed his PhD in 2018. His current research is broadly in the areas of image and video technologies. I hereby like to invite Professor Joy Prabhakaran to share his views and thoughts on the new age specializations for electronic and communication engineering. Over to you, sir.
Thank you. Hope I'm audible.
Yes, sir.
All right. Let me share my screen visible or not yet?
Not yet, not yet.
Now?
Oh, yes. It's just coming up.
Yeah.
Yeah, it's visible.
Has it gone into the full screen mode?
Yeah, once you click that, once more. Once more, sir.
Yeah.
Yes.
Okay. So thanks and nice to be talking to so many new young students who are kind of trying to find their way into the engineering fraternity, into an engineering way of life, I should say, rather than a career. My focus, what I'll be talking about a bit on video and a bit on VLSI, two fairly important streams these days. But rather than focusing on the technologies, it's something you all will anyway get to learn and will have to learn. I'm trying to give you a perspective on how things have evolved, and partly to address this question of how new streams kind of emerge and how streams merge, and how many of us I think many of us here in the panel today would find it little difficult to separate out what is computers or computer science, or what is electronics, what is mechatronics, what is robotics, what is IoT, as something with clear-cut boundaries. That's not possible, and there are reasons, and that's how things have to evolve. And I have picked up a few major developments in different decades and tried to kind of visualize for myself and for you how these things have happened, how these things have come together, and what we see today. On the right hand side, I'm showing things that we are all familiar with. But where did all these come from? And is it electronics? Is it electrical? Is it mechanical? Is it computers? It's a question with no a very clear-cut answer. That's my perspective. So on the top right, what I'm trying to show here, what this talks about on the top left, I've mentioned ENIAC, which is one of the early computers, 40s. It's interesting for various reasons, but one of the reason I would like to point out is that was a computer where you had to change the wiring to make the computer do a different job. So you rewired it to run a different program virtually. From that, if we come to the right hand side of this image, what we see is a situation of today's students, today's engineers, not just students, For them, and I'm not saying this in a cynical manner or something, because this is how it should be. For them, programming has come to be, for most people who write programs or create programs, programming has come to be something where you find the right thing and paste it into your solution. So it's become a kind of a cut and paste for a large number of professionals. So how did this transition happen from changing the wiring to make a system do a different job? And these are few of the major things that have happened along the way. So in 40s, information theory came up. One of the people I call my hero, Claude Shannon, and his work on information theory. 50s, we had the first transistor come up, but then there were computers in 50s which were these huge monsters, which were doing their job quite well. But then, like evolution of life, like dinosaurs and mammals, there were mainframes, and then there was this little thing, the transistor. Somebody had invented Shockley, Bell Labs. Things happened, and as the mainframe looked so dominant and so powerful, and that's what computing was all about. Into the 60s, and we see the transistor became an IC. That is, we had integrated circuits. There's multiple transistors on one die, and on the mainframe side at the same time, what happened was it was a legal decision. It was the unbundling that I mentioned here. That was when the government of the US decided, for various reasons, they decided that software and hardware need to be unbundled. So there were legal cases, there were technical reasons, all that was there. But from our perspective, the change that happened was the software. There could be software sold without hardware. Till then, hardware and software went together. The people selling hardware were the ones who were selling the software also. So you bought a system for an application. Suddenly, the system became the hardware became more of a platform, and people could start offering solutions on the platform, which the platform builder didn't think about it. And that really, in some ways, was this transition, this genesis of the software industry, because we today, since then, we have always been seeing this in the electronics field. That is, platforms get built and then they get used for things you don't imagine. The builders of the platform never imagined. It just keeps getting used for other things. On the communication side, 60s, the ARPANET came into being, where interestingly, one of the goals, and that's what led to the internet and all those communication systems that we see today. And please note this question on top. I'll try to come back to this as I end my talk, which is this again just a perspective, but the question here is, what does the internet carry the most? Like what is it being carried on the internet? What are the data? What are the kind of data? But coming back to ARPANET, which is the 60s, 70s that I was talking about, again, a lot of this derived from the US. The Defense Department, one of their goals was their communication system should work even if a part of their systems get bombed. And many of us would have read this. If we read this history, or when you study, you'll learn about all this. Hopefully, I don't know how much of history continues to be a part of the curriculum now. But yes. So one of the goals was that, and then a networking initiative got kicked off. In the 70s, TCP/IP was defined on the VLSI timeline, so to say. The microprocessor came to be. VLSI really started. Before that, it was integrations of lesser scale. So more and more transistors, more and more devices on a chip, on a chip. And then into the 80s, 90s, we see the IBM PC came to be. There were other PCs in 70s, 80s, but IBM PC, again, very revolutionary. The internet service providers came to be. VHDL, and VHDL is very interesting in the sense we are now reaching a stage. I mean, in the timeline, we are reaching a stage where ICs were being used to create systems, and those systems were used to design ICs. VHDL standing for hardware description language. What is V? HDL standing for hardware description language. I'm not recalling what V is. And so the whole concept of simulating ICs today, the VLSI industry is and that's where I'll talk a bit about jobs. That's where a lot of the high-paying jobs today are in the electronics field, and that is so much about design, and the design is all done using software tools, description languages, and simulators, simulate for the physics. In fact, VLSI is one area where technology is in some ways driving physics, in the sense one is encountering problems in this very large integrated devices that are being built at such low widths, 2 nanometer, 3 nanometer, 4 nanometer kind of technologies, where one is even discovering new things in physics, new rules are being created. So that's one stream. On the video stream, the way I have represented at the bottom, I'm skipping a lot of things just to bring out a picture. 80s, 90s, we come to a stage where there are digital representations and there are compression technologies. There are standards being defined where the standards said how video should be represented, how audio should be represented, and different compression technologies that need to be supported, which are all huge gains in terms of how much data is required for representing audio and video. And also MPEG definitions consist of how to transport it over different streams, different transport mechanisms. So all that coming into place. And in the next block, the 90 to 2000 block, things have gotten so mixed up. It is difficult for one to say which stream it belongs to. And if we take the World Wide Web, which came from CERN's, the Tim Berners-Lee, when we take the World Wide Web, it really is an expression of all these technologies, so to say. There is information theory there, underlying to make a World Wide Web possible. Computers, of course, communication, of course, computers, communication, everything running using a lot of VLSI. So we reach a stage where the technologies which were emerging have emerged and have started offering solutions where the components cannot even be separated out. So different things of that nature. I have mentioned Y2K as one of the things of the period 90 to 2000, because Y2K was very important for India software industry. It was a problem, the year 2000 problem, interesting problem in the sense the people who in the 60s built a solution on using a mainframe computer had to save on data, and to save on data, what they did was they used 2 bytes to represent a year. So 1997 would have been represented as 97, simply because nobody thought those systems will last into the 2000s. But when it came to 2000, or when it before 2000, suddenly everyone woke up, realized it's a huge problem, huge potential problem, because all the year computations will go wrong. That's what is popularly called Y2K, and we really rode on that wave, in the sense there was a lot of manual work, and that's where many of our marquee companies of today really got their explosive growth. And moving on, if we look at the period in since 2000, so many things have happened, and this kind of I'm talking about this also as an explanation, or as not an explanation, as an insight, or something to think about on when we say software, when we say hardware, how things have all gotten mixed up, because each technology, once it matures, it becomes a platform which allows a lot of other things to happen. And when a lot of other things can happen, there's a lot more activity happening. The platform, the underlying technology becomes more or less a commodity. So when work is happening, there's a lot of activity. After that, it's a commodity. It's given. It's taken for granted. It's like to use a very Bangalore kind of an example. When a bridge is being built or when a metro line is being laid, there's so much of construction activity happening. So much of that kind of activity happening. But once the bridge is done, then the activity is people driving over the bridge. So it's the drivers and some of the support systems, and then the users and that kind. So everything, including software, including so many elements of the software, like say an operating system. Operating system is a commodity. Not too many people working on it, but something like say the apps, the smartphone revolution really happened around 2010, little before that. And because it is so new, people are still discovering new things that can be done. People are still building solutions that can be offered. That is why one is seeing so much of activity in that area. While what's supporting it, the bridge, has been built earlier. But that also doesn't mean the infrastructure kind of activity is stopping. Like if we say we take VLSI today. Most companies are trying to get to 4 nanometer, 3 nanometer, and so many innovations have also happened. Like if an Intel is struggling today to hold on to its marketplace, its dominance, it's because an ARM has come which says we are a fabless designer. That is, we don't manufacture anything. We just give you the designs, you use it. And a TSMC has come up and says, we don't design anything. We build whatever you want. We build. So the paradigms change. Activities, new things come into being. Like on video, even today, there is so much activity happening on the OTT space because the newer distribution mechanisms have come to be. The newer, say each video distributor wants to distribute it over a different mechanism. I was recently involved with Sony Live. So much keeps changing there, and all that is, all those are activities where the need for people is kind of, unquenched. So to move on from this perspective and get a little bit into specifics, and since I'm talking about VLSI and video, I'll just use a couple of examples there. So on VLSI, what you see on the left, the image on the left is the first IC with two transistors. This is really, it's a lovely picture in the sense it reminds us of, in some ways our school days when we would have made things like this and shown it in a school exhibition, probably. But that was the first IC, first integrated circuit. So it had two transistors. By 2010, Intel was manufacturing i7 with, there's the image on the right, 2.3 billion transistors. If to me, I mean, others, again, it's a perspective. To me, this kind of encapsulate, this kind of captures how the mind-boggling changes have happened in systems which use electronics, systems which use ICs. This is where that power has come from, and then a lot of things we see are usage of this power. This is here, the representation here is of a processor, same with memory. And from a areas perspective, from a jobs perspective, if we look at VLSI, right from the design process, the problem specification, the architecture definition, the functional design, logic design, circuit design, physical design. There are tons of opportunities because there are tons of requirements. Companies are trying to hire and not finding people in these areas. And on the right are areas which, as senior, an older engineer, so to say, I started my career in the 80s or early 90s, 89. These are areas where one hoped India would have a much stronger presence by now. But that apart, I mean, that little bit of parochial patriotism aside, these are again areas where there is both continuous research of the cutting edge kind of research in terms of this is not just technology research, this is physics research. To technology implementation, all these areas require people because everything is changing. Like from 4 nanometers, if they get down to 2 nanometers, or I don't know if somebody is working on it, things are going to change. A little bit about again, this is a perspective on video, and this comes back to my question of what is the thing which is getting transmitted most over the internet. This kind of, I'm not going to run through this block diagram. This captures the algorithm, to say, of how video is compressed, and this kind of broadly, this algorithm is something which was present before in the 80s. The research in the schools, the labs would have been working on this in the 80s because early 90 a standard was established for this. The MPEG standard came out. So before that, all this work was happening. In 2000, so this was implemented those days on general purpose processors, general purpose controllers. In 2006, that period, I was kind of involved in a team which was working on building an accelerator for this component. Okay, a small part of it. This was all happening on the processor, an accelerator, VLSI, an IC for this, and obviously that was a time when the internet video was kind of exploding, smartphones were coming, so no wonder people were trying to build this. Today, what we see on the right is an IC which implements this whole thing. So the spread of from the 80s to it becoming an IC, technological changes driven by market requirements, and market requirements change as technology changes because newer services can be offered. All that kind of reflected in this also, and which let me answer the question I posed, because we are not face to face and I can't really probe you. One way of one perspective on what is the thing which gets transmitted most on the internet. Many of us would probably know that the maximum data that's getting carried on the net, 60, 70, 80% probably today, is videos. Okay, just volume of data. And the data at the final stage with this circle, what is showing, the VLC, variable length coding, the data is encoded using Huffman codes. So if we come back to this, the information theory aspects, Huffman was not here. Huffman was a little later. This is his his teachers, so to say. But the Huffman code is what is getting transmitted. So on a cell phone, on your phone, you're watching video. What is actually getting communicated are Huffman codes, which is something which the ideas were set in 50s, refined in 60s, and so on. I will stop with this with a final slide, which is actually showing a bit of my research now. This is an image processing application to improve the quality of images taken to detect a disease called retinopathy of prematurity. So what you see on the left is the original image. What you see on the right is the processed image. The idea being these blood vessels are to come out a little bit sharper. This is a ridge, which is a sign of the disease, which comes out with more clarity. And this becomes an input to AI systems for better detection of the disease. My work is on the image processing. If there are questions, I think we have time for later, so I'll leave it at this. I hope I haven't run over time. No, I think I'm okay. Thanks. And yeah, can we move on to the
Sure,
next?
sir.
I'm
Yes.
Thank you.
Sure. You can do this. You can stop the screen sharing. We take it over. Thank you so much for the insights and giving the advice to the students in terms of the video and VLSI for electronics and communication engineering. So yes, students, we move on to the next speaker, and we like to invite Professor Sinha. He has done his master's and PhD in electrical engineering from Institute of Science, Bangalore. He was offered a faculty position in the Department of Electrical Engineering at IISc, Bangalore. He set up a new parallel computing lab in the electronics engineering department, and most of his research efforts were directed towards applying the parallel and distributed computing techniques for industrial drive applications. He then moved on to the Center for Electronics Design and Technology, CEDT, at Indian Institute of Science, Bangalore, where he set up an embedded systems laboratory. The lab now has matured into a leading training and development center in the areas of embedded computing. He retired from IISc in 2011, and after a few years of preparation, he set up Lab to Market Innovations Private Limited at IISc. This initiative is seed funded by IISc, which also holds equity in the company. Lab to Market is innovating products and solutions to make the railways safer and more efficient. Today, we have Sir talking about, we'll have Professor Sinha, who will give us an insights on the ECE and the opportunities that are there for the students into it. Over to you, sir.
Thank you, sir. Shall I share my screen?
Yes, sir. Please go ahead.
Is my screen visible?
Yes, sir. You can go to the presentation mode. Yes, sir.
So I would essentially talk about what are the possible opportunities for EC engineers. I am of the firm view that this is the branch which has always been in need, in demand, and it will continue to be. Whatever shape the technology changes, EC engineers would be in demand always because of the two keywords, electronics and communication. We have been seeing that the technology also is being driven by these two, and it will continue to remain. However, I have to caution the students today that whatever you will learn in your 4 years of engineering program, that would be more like a foundation on which you have to keep building and rebuilding your knowledge base, because whatever you learn today will not be able to provide you a decent job after 5 years, because things in this domain are changing at a very fast, very rapid rate. There is a continuous need to learn and relearn. And unless you do that, unless you keep doing that, you will not be very relevant. In fact, I would say that if you don't do anything for 10 years, any new thing, you would be irrelevant. Nobody would want you. Now, this is a partial list of the domains in which electronics and communication engineers find jobs today. Circuit design is one thing that is needed in any product design. You have heard previous speakers talk about it. that how any product is a multidisciplinary thing, and electronic circuits are an integral part of almost every product. And I mean, the first speaker talked about an automobile 50 years ago, and the car was a purely mechanical device with all braking system, steering, engine, everything was independent mechanical units. And what were the amount of software in a car 50 years ago? Zero. Today, you take the lowest end car, it will have at least a dozen microcontrollers, thousands of lines of code. A high-end car will have hundreds of microcontrollers and millions of lines of code. So that's how things have changed now, and that's how this branch has become so critically important for any product development. Then VLSI is another area, which is a nanotechnology. So these two are, if you are more research oriented and in going into the core technology areas. However, a lot of people will find jobs into the signal processing. Again, you have heard previous speakers talk about variety of things being done. One thing was there, whether it is audio or video, it was signals that you needed to process, and that is a skill which is very much in demand as on today. Telecommunications has revolutionized the world, I would say, and still it needs EC engineers. Related to that are the two wireless communication and optical communications. These are also growing, particularly wireless communications are becoming more and more important, and it will gain more traction as the time comes. There's a lot of research also needed into that domain, plus a lot of product development. Then there are other domains which does not really maybe look very directly relevant, but power electronics, this requires EC background people for the control aspect of power electronics. Consumer electronics is anyway, that is something where it cannot do without EC. Of course, a consumer electronics, like any other product, will require expertise from all sorts of discipline. But again, EC is an important aspect of it. All kind of control systems they would require. Aerospace and defense, you have heard the previous speakers talk about it. There is a tremendous scope for this, and it is growing. It was emphasized that aerospace is going to be a big job creator in the near future, and so is the defense requirements. So these are the two areas, domains in which you hope to find jobs 4 years from now. Then mobile devices are, of course, becoming more and more sophisticated, more and more cost competitive, and again, this requires many more electronic and communication engineers than engineers from other branches. Robotics is again going to become a part of our lives in about 10 years time, I would say. There is a huge thrust I see everywhere. All universities are now pushing robotics in a big way. It is the government is also funding this kind of work. And yes, again, this will require large number of EC personnel. Industrial IoT has been there for quite some time, but it is becoming, I would say, almost like a commodity now, in the sense that everybody wants it. Everybody wants to monitor their whatever systems they have or whatever assets they have, then that needs to be monitored continuously. As I was informed about my background, we are working in the railway domain. We are currently focused on the railway domain. And one of the problems in the railway domain is that the assets are monitored manually and periodically. That leaves a lot of gaps where accidents can happen, and they do happen. So what we are trying to do is use these modern sensors and edge computing to see if we can monitor all the assets, particularly safety critical assets, continuously. So these are some of the domains in which you would find, and as you can see, you need to specialize yourself give a slight different orientation. The background that you require will be the same for all of them. The basics will remain all the same. But then you have to build on top of that, and you have to orient yourself to one of these areas, and then you can continue there for your lifetime. I would also take the risk, of course. Future prediction is always tricky, and one should avoid doing it. However, when I talk to young people, I find that they are more curious about what is going to happen to them 4 years after they complete their engineering, or 5 years from that, 10 years from that. So the way I look at it, the way I follow the research that is going on today, today we are only working about, with semiconductors and the conventional integrated circuits. That is not going to continue for very long, because there is an insatiable desire for faster processors, cheaper processors, and processors which take less space, they consume less power. So this demand, which is never ending, is now making semiconductor industries to go beyond semiconductor. Let me put it this way, and the traditional way of building computers, I would like to predict that it will change in about 20 years' time. The computers that you see today would become obsolete, and we will have very, very different kind of processors inside them. Quantum is one thing which has taken now good, I think already is visible. Optical processors are not so visible at this point of time, but if I were to make a prediction, I would say optical processors will perhaps win the race. So these are the domains in which you need to keep your eyes open for them, and because these will be something which will, if you have some expertise or if you have some experience in this domain, that will make you very valuable for the futuristic developments. So keep your eyes open for the developments in these two domains. One area which most engineers miss, or even engineering programs miss, is the analog electronics. I don't know why, because all the development has happened because of the digital electronics. We have made everything digital, and we are trying to make everything digital. It makes sense. However, we should not forget the fact that the world is not digital. World is analog. So while we do our computation and communication in a digital manner, at the sensors will pick up analog data, and actuators have to provide an analog signal out. So real world, if you have to do something in the real world, if you are not only in a that matrix kind of a thing, then analog electronics is unavoidable. Unfortunately, my personal experience is that the expertise in analog electronics is not there. I don't find many competent boys and girls coming out of the colleges who can, who understand analog electronics properly. It was also mentioned by the first speaker about the problem with EMI, EMC. That is a real menace, I would say, for every digital system, particularly low power systems. When you design things for aerospace or defense or railways, which I do, when I try to put something on the railway track, there is a 25 kV catenary up there. Thousands of amperes of current pass through, return current passes through the track, and it is hell for any electronic systems. So somebody needs to understand these things very well. And no wonder the few EMI and EMC experts which are available today, they charge by the minute for their expertise, because that expertise has become very, very rare. So I would say that if you want to look at an area which is evergreen, which is neglected today, that is analog electronics. Continuing with the future, what I would say that IoT with analytics. IoT is now passé. I think it's a standard. So newer and newer sensors are coming up. So sensor connectivity, that is already there. But can you do the computation at the edge itself and have a balance of the data at the edge and in the cloud? That is where it is, I would say, now. But 4 years later, it might be a little different. It might even get saturated because work is happening at the, I would say, with a very, very rapid race. So this is the immediate future, I would say, IoT with analytics. By the time you become engineers, it may not be so hot as it is today. Then many engineering programs only look at what you do in the laboratory, you do design, product development. If you look at the real jobs in the industry, there are many things other than product development which industries need. For example, procurement. And for a decent procurement process to be set up, the person must understand the electronics, the processes, and everything. We have our procurement head who is an EC graduate and an MBA. So this is another job, procurement, which is critically important for any industry. I would say, if there is a procurement is not there proper, your projects will get delayed. And then another thing is testing. We spent, at least in the domain I work, because I work in the area of safety. So we spend far more resources, far more amount of money on salaries in testing at equipment or a system than for developing it. This is an area where the numbers of I would say EC people is an enormous number of people are required for testing. Okay, of course, it is considered job-wise a little lower than development, but it is critically important. Okay, so you have the product, you have tested it, then you need to install it in the field. You have to install it and you have to do it. Now, I have put software development. Now, software, whenever you talk about software, you think of computer science department. I would say that is really not the case in organized companies like, or the products like what I develop, say, for example, IoT products. A typical computer science graduate will find it very hard to develop a software for an IoT application, because they are trained to work on a laptop or desktop or servers and that kind of environment. Whereas for embedded computing, we need people who can do the bare metal programming. There is no operating system. There is nothing. There is not even a single line of code there. So how do you program for that? That EC department will teach you, not computer science. Okay. So when I write here software development, I don't mean the software that will run on a server. I mean the software which will run on a microcontroller which does not have an operating system, which has nothing, not a single line of code. So how do you start it? You have to think about it. That is a wonderful expertise, and we pay a good amount of money for engineers who know how to do bare metal programming, who can program a board which has no line of software or no operating system mounted on that. Okay, then software deployment also requires expertise. That software has been written. How do you put it into the microcontrollers, make it work, and then test it? Again, I am coming to testing because this is, I have found, as the most important part of a product development. We keep testing, and we pay for the failures. if the test engineers, bring a system to us and they have created an environment in which it has failed, they are rewarded for that. Then, of course, there are other jobs like services that UK product has been deployed. Then the companies will need to maintain it for a few years, at least 1 year. Then software upgrades may be needed. For all that, you need EC engineers. Then I come to I have on the right hand side, I have mentioned some of the job titles which are given today. It can be not so interesting title as a software engineer, or it can have a fancy title like technical director, software analyst. But it is not that a particular job title may mean a particular job strictly. It varies. Different companies take different work from these titles. And currently on the left hand side, I have mentioned what is in my understanding, my knowledge. I could be wrong. As on today, the starting salaries for engineers for ECE typically from 60,000 to 120,000 per month in MNCs. But smaller companies like ours, startups, where a lot of jobs are there now or coming up, they start with about 30 to 60,000 depending on the person's skills and experiences. In US or Europe, you can expect a minimum starting salary of $2,500. You go up to $4,000 per month. So that is the current scenario to my knowledge. Okay. Now, work environment for EC engineers are not like always inside a air-conditioned room and all that. What you see over here is the actual photograph of an EC engineer testing the system in field. This is the work. Let me run that video. You see this track over here. The system that she is testing is the wireless operation of these points. So this will actually go to the driver, and the driver doesn't have to get down from his locomotive to set the route for himself. Okay, so now the way it is pointed, if it is left like that, the train will go straight, and otherwise the train will take a deviation. So that is what is set here, and we have developed a system to make process efficient. Now she would have operated it. The track would move, and it will change the route. Now it has changed the route, and then the signal here will also appear to indicate that it has changed the route. So this is the kind of system she is testing. And then her job is to, believe it or not, her job requirement is to make the system fail. The system has been done. It is doing its functional requirement. It is meeting. But can she create a particular peculiar situation in which it does not work or works wrongly? Okay, so that is part of the job, and that goes on before the system can be deployed. Now, final deployment would be in a locomotive like this. This would be with the driver, and this is the system through which they will operate. So don't expect that you would always be working in an air-conditioned, clean environment. This is a steel plant, Asia's largest steel plant in Ballari. The temperature here, where she is operating, would be 40 degrees centigrade plus. There would be dust, coal dust, and all sorts of things. So life is tough, but accordingly, the compensation is also good. Okay. So this is, I think I hope you got a glimpse of what to expect if you graduate as an EC engineer. And I will take any questions are there, I will take it later.
Thank you, sir. Thank you for this lovely insight. If you can stop the screen sharing, I'll take it up.
Yes, sir. That's what I'm trying to do now.
Thank you so much. So here we are, students, and like to move to the next presentation for the day. I'd like to invite Mr. Pankaj Bhande. He's a dedicated, resourceful, and innovative professional offering an extensive experience of around 20 years in the areas of IoT, artificial intelligence, digital voice assistants, chatbots, embedded systems, and mobile robotics, both in the hardware as well as the software, having used these skills in research and development, product design, education industry as an entrepreneur. He is a mentor by choice and he derives extreme contentment in helping people build capabilities. He likes to ideate and innovate advanced technological solutions and specializes in the following through projects. He likes to make teamwork engaging and interesting while not losing sight of the measurement of return on the investments. He comes with a high degree of discipline and involvement and likes to build self-sustainable people systems. I hereby would like to invite Professor Pankaj Bhande, and today he will be touching upon the topic interdisciplinary connect to stay in demand. Over to you, sir.
Thank you, sir. Am I audible, sir?
Yes, very much, sir.
Thank you. So I'm just trying to share a screen. It's just a video. Is it visible?
Yeah, it's visible, sir.
Yeah. Okay. So good afternoon, students, and thank you, Dr. Murthy and Shinde sir, for giving me opportunity to interact with the students. So students, I will just run you through what we do at Wiz Club, and because I'm obviously a recruiter also, I recruit people from engineering and various disciplines, various branches also. So this is just a video which shows what kind of an environment we have in the company. And when we say it is interdisciplinary, many of the expert speakers were saying that when you come into an industry, you cannot differentiate whether you are a electronics engineer or a mechanical engineer, or for that matter, maybe from any of the stream, even someone from commerce also. All of us work together and eventually it becomes a family, and it is all. So interdisciplinary connect is what I'm going to talk about. So this is an interesting concept which we have launched in the educational technology space, at tech space we call it as. And here we are trying to do the world's first event wherein children from school, you are completing your 12th, while I'm trying to take back what we have designed for children from school, how they are going to work together and trigger 1 million line of code. So if you have to create a setup which actually allows children from across the world to work together and trigger 1 million line of code. So while we are trying to understand what is an interdisciplinary aspect, this video will just help you out in terms of, so while I will keep talking when this video is getting played. So this is going to get recorded into India Book of Records, and this is about the Internet of Things Programming League. So where we call it as an ambient computing lab done on breadboard. So you now see simple electronic components like the capacitor, some wires. So this all falls into creating the first cloud IoT lab setup. So these are the raw components. Yeah, so you have these ultrasonic sensors, and then you have the displays. I have OLED displays and the ESP32 processors and breadboard. So now you see two of my core electronics engineer, Divya and Avinash, who are trying to create that setup at the electronics level. And then I have Ajib Sultan, who is the core mechanical engineer, who is trying to design the mechanical setup for this. So he's working in Fusion 360 and SolidWorks as a core area of competence in the company, and then whatever he designs gets laser cut using the machine. Then we have Amarnath, who is another mechatronics engineer, who is actually working now with Ajib. And then now you can see that Avinash and Divya, who are electronics engineers, and then Ajib and Amar, they actually did that part. And now that same setup of breadboards, which has all the electronic components completely handcrafted, is actually being set up by Divya and Avinash on that setup, which is being designed by, Amar and Ajib, who are the mechanical and mechatronics engineers. So this is how the setup looks like. This has around 1,000 plus IoT devices put on, breadboard, literally. And it's all core electronics and mechanical. And now comes the programmable portal. Now this portal itself is designed using HTML, CSS, JavaScript, wherein, while the people who have done it, there's Hari, there is, KP, then there is Sitara, Manisha, and then there is entire team of computer science engineer who have designed the portal together. And you can see that, this is a breadboard 3 online. These devices which you just saw, they are all online connected to the cloud. So now cloud is also coming, and even the portal which is designed is also hosted on some of the in one of the North Virginia EC2 server on Amazon. So these are the devices which are now available online. And what we see is, these are now the breadboards which are being powered on. And what you are able to see is that we are able to see that this entire setup has come to life because it is being powered up, and this is connected to internet. That is why I said these are Internet of Things, right? And every component is placed by my core electronics engineers, who are, the people who handcrafted this. And, this has so many. So if you look at this very black processor, it's an ESP32 processor, which has inbuilt Wi-Fi, Bluetooth, and a controller. And then, the rest of the components like OLED displays and ultrasonic sensors and servo motors and capacitors and wires, everything in handcrafted. And now this is connected to the Wi-Fi router. All components are connected, and via Wi-Fi router to the actual server, which is our EC2 server on Amazon Web Services on the cloud. So this is that setup which has all the components. Then we have another version of the same cloud IoT lab. This is a programmable setup. So this is Arup, who is the product manager and a electronics engineer, is a core PCB designer also. So he actually has designed now a set of PCBs. So just like you saw the raw components on a breadboard, now there are set of PCBs on the designed by using a Eagle software. So this is again something which helps you to do. And then there is a CAD version of it. So every PCB now is visualized in a CAD version. So again, which is done in Fusion 360. So this is a perfect marriage of, electronics being done as PCB design and then visualized into a mechanical software used predominantly across the world, that is Fusion 360. So it's again this. So, and then all those electronic components are now being held by a bridge. We call it as a WizGear IoT bridge, which is designed by Amar again in Fusion 360. So this is where mechanical and electronics come together, and every single piece of it has to work perfectly so that the PCB and this setup works together. And again, I must tell you that whatever I'm trying to show you is a setup which allows children across the world to trigger 1 million line of code that is going to get registered into India Book of Records. Okay, so he's doing the measurements and all of that. And now he sees that, yes, my design is perfectly done as per the PCB, and he's going to give us a thumbs up on that. So this is where the mechanical engineering part is done. And now comes those PCBs which you saw were designed by Arup in Eagle are manufactured here. So that's another setup which actually through which it goes. And again, you see my electronics engineer coming back into picture and then trying to solder those PCBs, right? So beautiful skill set to be able to solder PCBs with such a accuracy and where which component is positioned and all of that. So all this is actually going to help in terms of seeing the cloud IoT lab setup, which allows children to program the lab. So these are the manufactured PCBs. We all do this in our company environment, and all engineers from various branches actually work together to make this happen. So this is the manufactured setup for the various IoT devices which we have. And when we put together, now this setup is now getting created. So this is the other version, that is a PCB design version of the cloud IoT lab, which we have created. So these are some of the snippets of it. And this has a beautiful music behind the scene, but because I just wanted to take you through this journey. So now Ajib is designing the mechanical setup which will hold these, IoT bridges, and then Amar is ensuring that, the laser actually cutting off that entire setup happens. Now again, Sandeep, who is our mechatronics engineer, along with Ajib, is trying to set it up. So Sandeep will continue to do the entire setup assembly. Everything has to work together, right? Then only that entire setup will be programmable from anywhere in the world. So he is now trying to set up all these connections. And now this is the final setup for the PCB design version. So two versions, one is a breadboarded version, completely handcrafted. And this is that beautiful version, which is the PCB design version for this. So how children are programming across the world, together these devices actually in the lab. So they sit anywhere, the behind the scene pictures. So, this just is trying to showcase that, the data transfer from the client to server via satellite and undersea cable, right? So our setup is in Bangalore, but our server is in North Virginia, USA. So yes, it went to North Virginia via satellite, and it comes back to our IoT servers is in Dublin. So I'm holding it back here so that it connects to the Dublin server. And then it comes back to Bangalore, where you just saw the lab, right? Both the breadboard version and the PCB design version. So now the other option, instead of satellite, it can be the undersea cable. So these children are sitting across the world, any location. If they are connected to internet and they have a web portal which is designed by us, they can use any programming language in the world, and now they can program these hardware. So it starts with very young children to start with simple syntaxless blockly programming. So which is a IoT blockly. Now you can create conversational AI skills, that is chatbots and Alexa skills. So you program Alexa also as a device in this case. And then you are able to see the output, that is, it is trying to communicate with the hardware. So now these children have programmed this Alexa device, and it actually communicates with the breadboard version of the hardware, and it is controlling all the servo motors together. It's a beautiful view if you are able to see. So all the flags which we did at the testing, we did it on 15th of August. So, that was a time when we were able to test this system last year at an initial level. So then this is where, it actually, it is both ways. It is being tested at a chatbot level as well as the Alexa level. And now you are able to now program the same setup using Python as a programming. And you can see that, they are contributing. And then you can create web apps, which are again using HTML, CSS, and JavaScript. So if you look at it, it all is coming together, all branches, and you do not have a choice. You have to understand, if I have to design a web app, I must understand how the IoT works, how the cloud works, how the mechanical guy is going to do his or her job, right? And then the machine learning models are also being connected to the same hardware. So you build any machine learning model, you are able to see the output on the hardware. So it is a sentiment, and it is now printed on the IoT hardware also, predicted by us, right? So these things actually are all integrated together, and this is an example. So you are now engineering aspirants, want to become engineer. What we are doing is, we have created a program called Young Product Designers, and we take students from engineering and even from schools to work as interns in our company. And these two, siblings, Harshi and Rudra, their project is being selected in one of the competitions in ISRO as well. They have done 1,266 projects on this setup. They have done 1,266. So they did 49 projects using blockly programming. Then they did blockly simulator programs, projects for AT. Then they did web app, IoT web app, 124 projects with us. Then they built 81 chatbots projects actually. Then they built 90 machine learning models as a part of this. Then they built 155 Tinkercad CAD design projects. They designed 147 PCBs as a part of this. And then they programmed 165 C++ codes and then 185 Python codes. So together, then they worked on actual project POCs, proof of concepts, and they got the chance to work on together 1,266 projects in 18 months of time, right? So this is what that setup allows you to do essentially. So how does it work out? So then this is where, what goes behind the scene. What you just saw has so many components. This is where when I said that we as a team, although I was able to show you really very few members from my team because they're physically doing things, but the cloud team, the PCB design team, the the UX team, the UI team, the performance testing team, the testing team, the web framework team, the web server team, the IoT cloud team, any title which you read actually reflects one of the team member who is from a specific branch. You can see CAD design, SolidWorks and Fusion 360. You see, API testing, even our Zoom and Gmeet is also integrated. We have Google Analytics, so we have an analytics team, and then we have a project management team, and we have a PCB designing team, hardware simulation team, and all of that. So these people, they all work together seamlessly, and they are actually able to, work on such a complex stack. And this is where there is no syllabus when you come to the industry. You bring in all your interdisciplinary knowledge. You pick any branch of engineering, but you have to be equally good in as many other branches at a connect level. You may be specializing in one, but you should be actually equally good in others as well. And this is where all of it comes together. And then this is how the architecture actually looks like on the cloud. So these are the components which are there on the cloud, so which you are able to see. And together we actually run this complex architecture on Amazon Web Services. And then eventually, now this is the time where I am trying to showcase where is that 1 million line of code and how it is getting executed. So there are 2,859 programmable files over here. And the number of lines of code, so this is where you see that 1, 2, 3, 4, 5, 6, 7, 8. So almost 19 programming languages are used. How many files of it, how many lines of code, comment lines, even blank also is there, and total lines of code here. And then, it all goes together and this works together. Then only that cloud IoT lab actually sets up. So these are the files, the 2,859 files, which I'm trying to showcase here. And this actually is used to program this setup, right? So this is that setup. You will be able to see this in the news. It has taken more than a year for us to build this entire system, and a lot of engineering has gone behind the scene in this: CAD, PCB, hardware, software, embedded systems, cloud, IoT, you name the thing, and it is involved in this: machine learning, Alexa skills, chatbots, and all of that. And this is what is going to get recorded into India Book of Records. Only setup in the world, and we are the only company in the world who has built such a programmable setup for children to work with. And as I said, children have done 1,266 projects on this, and now they are going to become part of that India Book of Records, wherein together they will be actually doing that 1 million line of code triggering at a time, right? So this is why I'm trying to showcase this, is that this is how it works for me. If I go to a college and if I have to recruit an engineer, it is all about how open is that person. If you just say that it is all about computer science, believe me, they are just part of that system, right? They are not everything. They are just part of it. And if that craze is going to remain, more and more, believe me, you will see yourself in great difficulty, because great companies are not just built on computer science. Computer science is integrated into anything and everything in this world, and it should be done with all core branches. So core branches with computer science should be the approach, rather than, only computer science. And, that's where I love working with Dayanand Sagar University and working with Dr. Murthy, and, the way they are envisioning that, it is all about the interdisciplinary approach. And that's where you will see that, that kind of a benefit you will have here, right? So this is what I have, actually as a part of my presentation. Thank you, sir, for giving me the opportunity to, speak once again in this forum.
Thank you so much, Pankaj. Your presentations and your, the entire work that you do at Wiz Club is really amazing. It's good to see the practical implementation of a multidisciplinary approach. The way you look at electronics engineer, mechanical engineers, IT engineers, all of them put together, and the way the product is coming out at WizKit, it's marvelous to see. And we just hope that a lot of students from Dayanand Sagar University get to work under your internship activity and try and improve their skills to meet the requirements of what today you are trying to project under this multidisciplinary things. Thank you so much, Pankaj. So guys and students, we now would like to move on to something very interesting. And if you look at it today, another area which is upcoming, always going to be in demand for the next couple of years, is what we are talking about, aerospace engineer. People actually get misled. Sometimes people talk about aeronautical engineering. Aeronautical engineering is very different when it comes to aerospace engineering. And we are one of the very few universities in Karnataka or probably in South India where we are offering aerospace engineering. And to give you more details about the same, I would like to take the opportunity of introducing our next speaker for the day, Dr. Sharad Kumar Warrier. He has over 22 years of experience in various engineering organizations, including Quest Global, where he was the competency development head. He was leading the continuous improvement and technical training functions for Collins Aerospace, India, before joining Dayanand Sagar University in 2021. Alongside training providers, academia, and industry leaders, he has worked on academic curriculum that meet current and emerging trends and designed successful training programs tuned to the younger generation preferences. He is an alumnus of the Government Engineering College, Trichy, and holds an MTech and a PhD degree in mechanical engineering from IIT Madras. Professor Sharad Kumar Warrier is going to today give us the insights in terms of the emerging careers in aerospace. Over to Dr. Sharad Warrier.
Good afternoon, dear students, and very happy here to be with you at very exciting times for aerospace. And I would like to join all my distinguished panel members who have been talking to you about the changing trends. I do this talk very often. What I find is that every batch of students, when I talk, there is something new I need to talk about. The simple reason is that aerospace is today in a time in history where it is evolving at a very rapid pace. And over the next 15-20 minutes, what I wish to do is to give all of you young students a glimpse of what is there, what is changing globally, and whether it would be of interest. To start with, let me tell you that aerospace industry is very particular about the safety. It is a highly safety-centric industry. Along with that, it needs to be economical. And of late, one word we hear very, very often is sustainability. What are we doing to the planet? As aerospace engineers, are we going to create a planet which is not sustainable? How are we going to be responsible towards the future generation? So last 30, 40, maybe 80 years, we have had aerospace engineering using fossil fuels. But today there is global warming, climate change, and many other challenges. So how is aerospace industry going to adapt to all of this? And therefore, the first trend I would like to talk to you is about the sustainable aviation, which means the jet engines that have been there. We need to see lower emissions. And alternatively, we need to have electric propulsion, battery-based, hybrid propulsion, as well as hydrogen-based powered flight. So these are the emerging trends which creates many areas both for research as well as development. The second topic, which you have heard many of the distinguished panelists talk about, is about testing, certification, and what we call as airworthiness. Whenever you enter an aircraft, there is a certificate which is given that this aircraft is safe for flight. And that involves many processes, many tests are done. And this industry sees a lot of emphasis on certification and airworthiness. The next major trend that is affecting globally is called Industry 4.0, the fourth industrial revolution. If you recollect, the first industrial revolution was with the locomotive, the steam engines. And powering that is a new trend called additive manufacturing or 3D printing. This used to be something which was not there in aerospace industry, but of late, we are seeing even in the space industry, the latest space flight by Elon Musk, they have used additive manufacturing for the nozzle of the spacecraft. So to that extent, we are seeing this revolutionary technology is going to change the face of aerospace. The next point I talk about when we talk about aerospace is greener materials. People are saying it is not enough if the material is manufactured is safe. But what about the employees who work on that? The shop floor workers, the raw material handlers, the people who are working on the mining, every person should be safe. So green materials, green manufacturing is putting a lot of emphasis on retiring, replacing, changing the conventional existing materials to find new materials which are acceptable to the public, which are acceptable from a chemical pollution point of view. And therefore, this is a big challenge for today aerospace engineers, that how do I change material to make it more green? I spoke to you about greener operations, which means that my flight, my handling, I should not use too much energy, and all of this creates many, many areas for research and development. The next trend that we are seeing, you can see that it's no longer the government-based organizations which are into space exploration. There are many private players and they have been quite successful. So the next big trend is that the privatization in space and defense. Along with that is the entry of startups, the people who are having their own entrepreneurs who set up their own establishments. There is a lot of emphasis from the government and other players to provide them the funding, to provide them the expertise, encouragement, opportunities, so that youngsters, the new generation people are able to enter the space and defense sector. So at the bottom, you see that these are areas, as we can see, are not necessarily having something directly to do with the computational methods, but it is about advanced materials, advanced manufacturing methods, and all of us are on this planet, so we need to talk about energy conservation. The next, I wanted to go a little deeper when we talk of electric or alternate fuel, why this area is catching so much of attention. First of all, it is interdisciplinary at a very fundamental level. We are talking of fundamental physics, fundamentals of chemistry, how energy is produced, how energy is consumed, laws of thermodynamics. I'm sure as you would have studied during your school days as well as during +1 and +2, thermodynamics and many such subjects. So this is the area where all of that is practically applied. The next two concepts is because all of these aircraft have to eventually fly against gravity. So people say, how much power is there per kilogram? It is not possible for me to take a 500 kilogram or a 1-ton battery and say that I need to fly for 5 hours. So how can I ensure that my energy density is so high that I have a very high power per kilogram? So most of you are cell phone users. You'll be knowing that when you use a cell phone, how long will the battery last? And you cannot have the size of the cell phone so big that the battery will last, but it's not convenient. The next topic is, what if an aircraft lands at an airport? How long will it take to recharge or refuel when there is a new alternate fuel? Earlier, it was very convenient. The jet aviation fuel will be put into the aircraft through the nozzle. The aircraft will be having around 30 minutes, during which time possibly the passengers will get down from the previous flight and the new passengers will get on, and there was enough time. But in the new time, when you have alternate fuel like electric battery or a hydrogen battery, how will you recharge and refuel? So that creates a lot of logistic challenges. Where are you going to store it? How will you transport it? How will you load it into the aircraft? How will you make everything safe? It should not catch fire. Whatever is being done has to be done in a safe way, as I mentioned. So these are all very fundamental engineering challenges which were not there possibly even 5 to 10 years back. These are all very, very new challenges, especially when it comes to electric powered aircraft. The next big trend which is hitting our industry, which is really an opportunity, is the real entry of smaller and medium-sized passenger aircraft, which means I don't need a very big aircraft runway the size of a Delhi International Airport or a Bengaluru International Airport. With a shorter runway, the aircrafts will be able to take off and land, such that I'm able to have my aircrafts and the airports in smaller cities, in the tier 2 and the tier 3 cities, And the air connectivity in the country will be at a completely different level, which is there in the Western world today. But that is an opportunity, untapped potential, which is there in the Indian aviation sector. And whenever you need medium-sized aircraft, you need the servicing, you need the maintenance, you need to have the operational readiness. So you can have smaller cities also having their own runways. So this is a new trend. At the bottom, you can see that again, the multidisciplinary areas are chemicals, how to handle chemical engineering, electrical power, electronics, and of course, mechanical engineering. So aerospace is one area where you will tend to see all of these merging together. The other big trend is the rapid speed of urban air mobility and autonomous flight. So already there are a lot of tests happening on autonomous cars, autonomous vehicle. Now, what we are saying is there will be something called air taxis, which are vertically taking off and landing. You can imagine the terrace of your apartment or your building, or the ground where aircraft air taxi terminal is there. So you can go there and the taxi will pick you up and drop you where it needs to go. There will be sky ports where there will be possibility for people to change from one location to the other. So these are certain developmental areas. The next is the government has put a lot of emphasis on air adventure, air sports and recreation. So this will create many opportunities in smaller aircraft, parachute, parasailing, and many other lighter aircrafts, gliders and so forth. Coming to autonomous flight, we can see that there have been many pilotless aircraft which are being experimented. And what is the safety? How much can we rely on this? The next topic is these aircraft are connected and self-aware. Imagine that you are already flying and there is a weather issue. You need to be rerouted. And at that time, the connected aircraft concept allows a pilot to get the latest route that is safe for that person to take. There has been a lot of interest, and you must be reading a lot of news articles, especially in the Indian context, with respect to encouraging drones and unmanned aerial vehicles. Sometimes we like to technically call it as aerial robots because they can be used for multiple missions, whether it is for transporting food or medicines or reconnaissance, or just to as a defense methodology. You know, these are some areas where drones and UAVs are extremely important. And programming, testing, and avionics and digital electronics, these are the areas which merge into this particular domain. Coming to the next area for aircraft industry is what we call intelligent aircraft. So with the advent of the IoT and the artificial intelligence and many such developments, there is an emphasis on the fundamental sensors. So what are the right type of sensors which can withstand the high temperatures, which is there in a jet engine, for example, high pressure, high performance sensors, which are very reliable. If there is ice formation in flight and the pilot is not able to understand it or take some action, it is a very dangerous thing because the pilot or the aircraft does not know what is the right speed at which the aircraft is traveling. So these sensors cannot have ice formation. I'm just giving you some examples of how much physics and how much technology is involved just to develop these sensors, which are aircraft meant for aerospace applications. The next topic is about wireless technologies. As Dr. Suresh Nagesh was mentioning, there is a trend to replace all the wires which run literally in a large aircraft into kilometers for all the sensors, the power that is being distributed, and the signals that are being acquired. So can we have wireless technologies, especially to give the control signals as well as the sensors? So this will be able to reduce the weight as well as the complexity of the aircraft. The next we talk about is prognostics and health management. You have already heard about digital twins. What we mean by this is how long will this aircraft fly? Now, suppose you buy a cell phone, probably you will use it for around 3 years. If you buy a bike or a car, probably you may be using it for maybe 5 to 10 years. But if you are a big airliner and you have bought an aircraft, you are going to operate it for around 30 years or more. So how is this part reliable? Can I still fly it safely? So there are health indicators which will tell you if a part is showing high temperature, high vibration, there is a leakage of oil, the pressure has reduced dangerously, or something is abnormal. There are methods by which the aircraft technicians will be able to get this information even when the flight is in the air. Literally, by the time the aircraft lands, all the technicians, the repair method, the repair personnel are ready with their methods to give the required interventions. So this is the fast speed at which the prognostics and health management is progressing. The last topic there is very exciting area, which is called augmented, virtual, and mixed reality, which means using the augmented reality, you are able to imagine a person who is getting trained as a pilot or who is getting trained as a drone operator. They can do the simulated training about different terrains, how to fly in bad weather, how to fly in the night, in adverse conditions, where there are mountainous areas, and how do you navigate. So you can use the augmented reality using those special glasses that people wear or some other methods to give them the training. So aerospace is one area where this methodology, whether it is a high performance pilots, combat aircraft pilot, or for that matter, any other operator in aerospace, they can get trained. And this is especially useful for training the air maintenance personnel. Suppose there is a new aircraft and there's a very experienced maintenance person, let us say has been working for 10 years or 15 years. Suddenly there is a new aircraft and there are people like this spread all over the world. Now, how do you provide them the training? So with the augmented reality, these people will be able to open the aircraft at the right location, where to fix it, because they have been trained using the augmented and virtual and mixed reality. So you can see that the physics of the repair methodology with the digital processing and the software can be used to use literally a globally distributed aerospace. And I can tell you that this particular mixed reality can be in multiple languages. So if you are, even if you are a English speaking person, you can provide that instructions to the repair personnel in any language all over the world. So these are some exciting areas for intelligent aircraft and aerospace. Coming to the seamless passenger experience, you can see that at the bottom of that picture, there is a person who is walking into the airport with the baggage and directly going to the flight without going through a manual intervention. So this whole process of touchless travel, the aircraft security zones are being redesigned, how you do the baggage check-in, how your baggage will be handled, how your security will be handled, the ticketing. And there is an artificial intelligence for your experience. You may like to have a certain temperature or a certain color. So there are ways in which your experience can be customized using your artificial intelligence data. The next one is a very, very crucial thing these days is about cyber security. Can somebody hack into your system, into the aircraft system, or take down the airport computer? It is very disastrous. So during the development, the new methodology is called DevOps, is being augmented with a new methodology called DevSecOps, which means during the software programming itself, you take care of the cyber security so that no threats are being handled. The next one is called the blockchain, whether it is aircraft assets, the maintenance to be done, flight operations. You can use blockchains to make all of these a seamless experience. Now, to do skills which are required for this, you can appreciate that a traditional aerospace degree would be difficult. So what has happened with the national educational policy, the time at which you are all going to become students, is that students are going to be given more flexibility and choices to choose their electives, which subjects they want to choose, and so forth. So with this kind of a more flexibility given to your talent, to your interest, you can augment your aerospace experience along with other areas, whether it is a commerce or the blockchain, in order to be able to get a very, very good niche area skill by the time you graduate out. I can see at the bottom, you can artificial intelligence, the machine learning, cloud computing, all of these are very relevant in order to make the above experiences very simplified and valid. The last two slides I have are on the exciting areas in defense and space. Today, the defense platforms are getting upgraded in the Indian Air Force as well as in the Navy and many other domains. And we need a lot of high performance aircraft and missiles for the Air Force, Army and Navy. We need combat drones, and also we need drone operations. So how do we use these drones effectively? And you can see in the modern warfare, drones have become very, very important. Coming to the satellites and spacecrafts, one trend is about reusable launch vehicles. So earlier, the launch vehicles would be going into the sea and it would be a big waste. But people are saying, can we use the lower stages or the last stages? Can we recover it so that the cost of these operations comes down? And we are also talking in India about manned spaced missions and planetary explorations. So these are all at a very fast pace. Things are moving, and not just in India, but there are many global opportunities in the emerging aerospace and defense. And you can see that post the armed conflict in Europe, which is currently happening, suddenly all the people had to take a look at their defense aerospace strategies. The kind of new terms that we are hearing about, you can see on the screen: loitering munitions, anti-artillery capability. You can use a tilt rotor aircraft for a longer range along with speed instead of a helicopter. That's something people are exploring. So these are vertical takeoff aircraft, so that it takes off vertically, and after that the just like a helicopter, it will go up. After that, the rotor becomes horizontal and then it will push the aircraft. So this is a tilt rotor aircraft configuration. People are talking of a space command in addition to the Air Force. So they say that the space is also a very important area of defense. People are talking of hypersonic systems, which are beyond supersonic, very high speed systems, which will give tremendous competitive advantage to any country. So we are talking of in India, especially about advanced multi-role aircraft, airborne early warning systems, and especially in India, we are really looking at upgrading the radar systems and the electromagnetic spectrum and the electromagnetic interference and compatibility, EMI, EMC. So these are all multiple areas that aerospace is offering. And to stay competitive, we depend on the young generation. We depend on young students like you. The people who have been in the system are also having to adapt, but you have an advantage because you have the time to learn and embrace all these opportunities. So keep innovating, keep learning, keep networking, and I'm sure that it will be an exciting career. Thank you.
Thank you so much, sir. A wonderful thought process and an insight for the students to understand on the aerospace engineering. We do see a great demand in terms of the jobs coming in from this area. And I'm sure that the participants who are there with us, who had all the patience to wait across to hear about aerospace engineering, will definitely be satisfied with the information being shared with them. So dear students, and especially the ones who have already enrolled with Uni-Gauge and have paid the registration fees for the common key examinations to you, we would like to give you a special message. We have the Dayanand Sagar Scholarship Admission Test, which is special scholarship examination for Uni-Gauge registered students, being arranged on the 14th of June. The registrations for this examination is open. And let me tell you, all the students who have registered with Uni-Gauge by paying the fees to the Uni-Gauge and have got their unique number, with that unique number, you could fill up the registration forms with us, as there will be no examination fees being charged to you. There is no registration fees at Dayanand Sagar University if you are coming with the Uni-Gauge registration ID. And with that ID, you will be able to take up the scholarship test. And in case if you are able to clear the threshold score with the scholarship test, you will be able to get the special scholarship fees from Dayanand Sagar University. The special scholarship fees is much lower than the actual fees that is being awarded to Comet K students. So if you want to really work hard on the scholarship test, the benefit is you will get a special scholarship fees, which is going to be much lower, and that gives you the benefit of the fees in for the next 4 years. So I would wish that all of you do register for this examination. and take the examination on the 14th of June and put in your best effort so that you are able to clear the threshold score and we are able to offer the scholarship to you. For more details, please do check your emails, please do check your WhatsApp message, and you will be able to see the registration details being sent out by Dayanand Sagar University admissions team. With this, we come to the end of this wonderful webinar organized by Dayanand Sagar University on these various technologies, where we talked about the new age mechanical engineering with specializations. We talked about the new age specializations in electronic and communication engineering. We talked about the complete diversity of the aerospace engineering and how these areas are going to help you to stay ahead in the competition. We at Dayanand Sagar University, we have got some industry and company sponsored labs available at our facility. We would like to invite the students to come and see those labs, come and see the way some of our students have been able to create their own companies or launch their own products through these labs. And we would really appreciate if you could come down on one of these days and see all of this, so that you are able to understand the kind of efforts put in by this university to give you all the required tools so that you can look forward to a successful career with us. With this, we come to the end of today's session. I would like to thank all the distinguished speakers and the Honorable Vice Chancellor, sir, for being available on a Saturday in the second half to guide the students, to guide the aspiring students from Uni-Gauge to look forward to an aspiring career. My sincere thanks to all the speakers. And very soon we will be coming up with some more exciting series of webinars and topics. I would want all of the students who are there to keep a watch about this on our website or on their emails, and we will be able to help you with all the questions that you have related to choosing the field of study for yourself. So thank you so much, and a big thanks to all the organizers from the admissions team of Dayanand Sagar University who have been working relentlessly with the Uni-Gauge team to make sure that these webinars go up successfully and the students are able to take the advantage of this. My sincere thanks to all of them, and we look forward to seeing you soon for our next webinar series. Till then, stay safe, stay healthy, and be informative. At any point of time, any questions, please log on to the website. There are helpline numbers given, and our career guidance team will always be available to guide you. Thank you. Thank you so much. Goodbye.
Yeah, thank you, everybody.